Good day, learners. I'm Aries Bulaclac from BSME 3B, and together we will study about the AC and DC machinery.
Receiving incoming transmission.
First, let's have a quick introduction. So, electrical machine generalization. So, rotating electrical machines are also of two types, AC and DC machines. In DC machines, the stator is used as a field and the rotor is used as an armature, while reverse in the case of AC machines. So later on, we will further discuss AC machines, DC machines, stator and rotor, and armature and field posts. Rotating electrical machines are widely used for the purpose of converting energy from one form to another. So the two most frequently used types of such machines are generators and motors. So what does it mean converting energy from one form to another? So the generator converts mechanical energy to electrical energy, while the motor converts electrical energy to mechanical energy. So for today, we will only focus on the generator. Okay, generator. So an electric generator is a device that converts mechanical energy obtained from an external source into electrical energy as the output. So, it is important to understand that a generator does not actually create electrical energy. So, instead, it uses the mechanical energy supplied to it to force the movement of electric charges present in the wire of its windings through an external electric circuit. So, this flow of electricity charge constitutes the output electricity current supplied by the generator. This mechanism can be understood by considering the generator to be analogous to a water pump, so which causes the flow of water but does not actually create the water flowing through it. Okay. There are two main parts of a generator. So first, the armature. This is the power generating component in a generator in which the output voltage is produced. So it is made up of a laminated steel core of rectangular cross section consisting of coils of copper wire wound around it, so which is called the armature windings. The armature winding is insulated to avoid direct contact of the coil with the core. So the armature is used to communicate between two magnetic fluxes. Next is field poles. These are set of pairs of electromagnets or permanent magnets which are even in numbers. So each consists of laminated steel core or rectangular cross section consisting of coils of copper wire wound around it, so which is called the field windings. So poles in generators are responsible for creating magnetic flux density, which is an essential requirement for inducing EMF in the armature winding of the generator. Poles always exist in pairs, so number of poles is always a multiple of 2. Note, so as you can see in this diagram, so in a DC generator, most often the armature is the rotating mechanism and the field poles are stationary. Another one, as you can see in this diagram, so in an AC generator, especially those with high voltage output, the field poles are made to rotate in a stationary armature. So the current in armature winding of all generators, whether AC or DC, is always alternating. As I mentioned earlier about the rotating mechanism, so a rotating mechanism is called a rotor. So the rotor is generally used to provide the power that is generated. And another one is stationary. So stationary part is called a stator. So the stator receives the energy inputted into the generator by producing electrical power output. Now, let's move on to our main part of the discussion. So the difference between AC and DC generators. So first, we will define AC generator or alternating current generator. So in alternating current generator, the electrical current reverses direction periodically, and the coil through which the current flows fixed while the magnet moves. So the AC generator does not have commutators and it have a slip ring. In AC generator, so the conductor is formed of a coil of wire placed inside the magnetic field. The conductor is manually rotated within the magnetic field. Then this generates an alternating EMF. Then the alternating current needs to be transmitted from the conductor to the load, which is the system requiring the electrical energy to function. The load and the conductor are connected by a slip ring. A slip ring is a connector which is able to transmit electricity between rotating portions of a machine. It is made up of a ring and brushes, one of which is stationary with respect to the other. Here, the ring attached to the conductor and the brushes are attached to the load. Current is generated in the rotating conductor, passes into the slip ring, which rotate against the brushes. The current is transmitted through the brushes into the load, and the system is thus powered. Now, let's move on to the working principle of the alternating current generator. So as you can see in this layout, so the direction of the current changes with every half turn of the coil. So as one side of the loop moves to the other pole of the magnetic field, the current in the loop changes direction. This type of current which changes direction is known as alternating current. So next we will play a video for you to further understand what I am explaining earlier.
Consists of a rectangular coil of insulated copper wire. The coil is placed between the poles of a strong magnet such that the magnetic field is perpendicular to its arms AB and CD. The ends of the coil are connected to two rings which are separate from each other but are mounted on the same axle. Two carbon brushes on the outer side of the rings connect the coil to the galvanometer. A galvanometer is an instrument that can detect the presence of current in a circuit. The pointer remains at 0 when there is no current flow in the circuit. The pointer can deflect either left or right of the 0 mark depending on the direction of the current. When the coil rotates, the ring slides on the brushes. Springs are loaded on the other end of the brushes so that they always maintain contact. Let us understand the working of a generator. When the axle attached to the two rings are rotated such that arm AB moves up and CD moves down, the magnetic field associated with the coil changes. This changing magnetic field associated with the coil induces a current in the circuit, a phenomenon known as electromagnetic induction. By the application of Fleming's right-hand rule, induced current in the arms is from A to B and from C to D. Thus, the induced current flows from the path ABCD in the coil. After half a rotation, CD moves up and AB moves down. By applying Fleming's right-hand rule, the direction of the current in the arms get reversed. So, the induced current is in path DCBA. Thus, the direction of the current gets reversed after every half cycle. Such a current, which changes directions periodically, is called alternating current, abbreviated as AC. The device which generates AC current is called as AC generator.
Now, we will define DC generator or direct current generator. So, in direct current generator, the electrical current flows only in one direction. So, the coil through which the current flows rotate in a fixed field. DC generators have commutators. So, what is a commutator? The commutator reverses the current direction with each turn serving as the mechanical rectifier to convert the alternating current from the windings to a unidirectional direct current in the external load circuit. So DC also have a split ring. In DC generator, a simple DC generator is constructed the same way as an AC generator, except that there is one slip ring which is split into two pieces, called a commutator. So the current in the external circuit does not change direction. The split ring commutator accommodates for the change in direction of the current in the loop, thus creating direct current. So current going through the brushes and out to the circuit. The current in the loop does reverse direction, but if you look carefully at the 2D image, you will see that the section of the split ring commutator also changes which side of the circuit it is touching. So if the current changes direction at the same time that the commutator swaps side, the external current will always have current going in the same direction. Now, let's move on to the working principle of the DC generator. So, consider a single loop DC generator. In this, a single turn loop ABCD is rotating clockwise in a uniform magnetic field with a constant speed. So, when the loop rotates, the magnetic flux linking the coil sides AB and CD changes continuously. So, this change in flux linkage induces an EMF in coil sides, and the induced EMF in one coil side adds the induced EMF in the other. So to further understand what I'm explaining right now, we will watch a video according to the working principle of the DC generator.
Let us see what happens if the rings are replaced by a commutator, which are split rings. When the coil connected with the commutator rotates, one of the split rings is always in contact with the arm which moves up, while the other is always in contact with the coil which moves down. By applying Fleming's right-hand rule, we find that the induced current in the coil is always in the same direction. Hence, a unidirectional current is generated. The current which is always in one direction is called direct current, abbreviated as DC. The device which generates a direct current is called DC generator. The advantage of AC over DC is that it can be transmitted easily over large distances with minimal loss of energy. The generators have a large number of turns of insulated copper wire wound over a soft iron core and is placed between electromagnets for enhanced performance.
Earlier, in the videos that we watched about the AC and DC generator, you may have noticed about the Fleming's right-hand rule. So, the purpose of Fleming's right-hand rule is to find the direction of induced current when a conductor moves in a magnetic field. So, in Fleming's right-hand rule, it states that if we arrange our thumb, forefinger, and middle finger to the right hand perpendicular to each other, then the thumb points toward the direction of the magnetic force. The forefinger points towards the direction of the magnetic field, and the middle finger points towards the direction of the current. Today, I hope you learned something. Thank you for watching and God bless.